Hello everyone, and thank you for joining our SOLIDWORKS Flow for Thermal Analysis in Mechatronics and PCB Design webinar. We have two presenters today, Drew Buchanan, our simulation specialist, as well as myself, Mark Talbot, the electrical and PCB specialist. And today we're going to be looking at a little bit of the SOLIDWORKS PCB software as well as flow simulation in the mechanical environment. So Mark Talbot, I'm your electrical AE at Fisher Unitech. I've got a couple of years experience in motor design and elevator systems and industry, as well as a master's in power electronics and motor design. So essentially when it comes to your product design, validating that design, getting your board to function and fit in your environment, we really have a whole suite of product that can address these needs. So going from PCB design into bidirectional communication to the 3D design, once you're there, you can handle all the host of tools that are available, PDM, Visualize, Composer, as well as your simulation products. And in this case, we're going to take a look at that thermal validation in this process. So for PCB design, we actually offer two products. One is called SOLIDWORKS PCB. It's powered by Altium. It has your schematic capture, your board layout, as well as that collaboration between the mechanical and PCB environments. Our second product is called SOLIDWORKS PCB Connector. And because SOLIDWORKS PCB is powered by Altium, we've partnered with them extensively, and we're able to give those with an Altium Designer existing seat that collaborative capability as well. So moving beyond the exportation of files, but actually bidirectional communication, being able to move components in either environment, board fit, and so on. And those both communicate with a collaborative server, which again stores the instructions for building the models in both environments, so it recognizes those changes in both environments as well. So what's the point? Why have a PCB tool? Why go about collaborating between PCB and mechanical? Well, essentially, the mechanical designer, he's usually responsible for things like the board outline, maybe mounting hole locations, collision of components, parts placement, so critical parts placement. You can think of your connectors, your push buttons, your screens, and ultimately even things like thermal validation. So if the mechanical designer is responsible for these things, rather than him creating a secondary document and having to then relay that over to the PCB designer to recreate that work, why not be able to allow him to natively influence that information? And of course, today we're going to assume that we've got that board outline, we've got that collision information, our parts placed and routed, and we're going to focus in on thermal validation. So essentially, is our circuit going to behave due to temperature the way that we want it to? Do we need to refine any of the assembly or the board? So with that, I'm going to go ahead and throw things over to Drew to go ahead and introduce himself as well as the tools that we'll be looking at. Go ahead, Drew.
Thanks, Mark. Welcome, everyone. My name's Drew Buchanan. I am the simulation specialist here at Fisher Unitech. I deal with everything pertaining to FEA, CFD, and injection molding, as well as some of the other simulation applications out there. I spent 8 years in industry prior to entering the reselling industry, specifically focused on thermal management, focused on electronics enclosure for tooling systems for the power industry, as well as spending a little bit of time in the biomedical industry. So what you're going to be seeing today, Mark's going to be giving you a demonstration of PCB, and then he's going to sort of feed over two simulations to me, and we're going to run within flow simulation to sort of run a heat transfer scenario. It's really important to note you can do a lot of different things with flow simulation. Flow simulation is an integrated CFD code built into SOLIDWORKS, and what we're going to be looking at in today's webinar is everything within flow simulation and electronics cooling. So specifically on the electronics cooling side, we're going to be using the PCB generator as well as an expanded material database to sort of solve our thermal problems. So here's kind of a nice overview of what we're going to sort of accomplish in flow simulation. So we are really going to be looking at an engine and a PCB with an IC, and we want to monitor the temperature. So we're going to utilize SOLIDWORKS Flow simulation to determine temperature of the motor and the PCB. I'm going to show you how easy it is to set up these scenarios. So some of you have done physical prototyping or physical thermal management. You're going to see how efficient it is to use the software. And lastly, you'll sort of see how easy it is to run these scenarios. I have a couple different scenarios we'll actually be taking a look at.
So with that, this is Mark again. Let's go ahead and jump into SOLIDWORKS PCB and get this process started. So essentially what we have here is kind of an oversimplified encoder circuit for an AC motor. And what we also have is our board designed here as well. Now, because of our environment, we've actually have the 3 phases for the motor supply feeding through these slots, so it's a very noisy environment. So what that means is because of our signal to noise ratio, we need our IC to be basically outputting optimally to make sure that those encoder signals can be read. And so we've added some shielding there as well, and we need to make sure this performs what the thermal kind of characteristics of that IC is to make sure that we can get the signal to noise ratio that we need and to really validate whether our board can even be located in that area. So that's kind of our first scenario. And let's go ahead and jump over to SOLIDWORKS. I've basically pushed this design from our PCB design tool into the collaborative server. And from there, I can pull this design into the mechanical space. What you see is that copper information actually gets pulled in and built as a part as well, which is going to really benefit our thermal analysis in this case. And so from here, I can actually refine part placement. I can move parts from another side of the board. I can actually edit my board shape and my hole locations in this board as well. And again, that's bidirectionally communicated into both SOLIDWORKS PCB and the mechanical side of things. So this is our assembly. Our 3-phase and ground are going to feed into here, creating that noisy environment for us. And ultimately, this motor is also going to act as a bit of a heat generator as well. So we'll need to see what that IC is going to be built up as. Now I know if this is going to fail, if we don't get an optimal kind of solution for our temperature for our IC, I know what I'm going to need to do is move this board into a less noisy environment. I could then remove that shielding, for example. So what I've gone and done is I've already built that situation up in SOLIDWORKS PCB. And so I could send over that shielding case from the mechanical environment to be used in some thermal validation. And I can also go ahead and push this to the server as well and have this sent over for another location, for example. So I'm going to go ahead and just send a message here to the mechanical side to go ahead and use this as well for some more thermal analysis for case 2. And I can post that to the server. It'll build the instructions there for this model. And I can go back to my mechanical tool. And what you'll see is if I go into the board view, I get a message of the changes. I can view those changes, accept them. And it's going to go ahead and build that new model for me in my assembly and throw it in the upper level assembly as well. So a really good tool for communicating that information in both environments. And ultimately, this will allow us, again, to get that information in a mechanical tool where we can do that flow simulation, that electronics cooling simulation. So we'll just have this build, and then right after that, we'll preview our assembly and send things over to the simulation side of things. And just a reminder at this point, if there's any questions, go ahead and send those to us in the chat, and we'll go ahead and answer those at the end of the presentation. So Drew, if you'd like to take things away.
Yeah, thanks, Mark. Can you make me presenter? Thank you.
Yep.
Okay, great. So after Mark, kind of the easiness in thinking about this, he sent me over 2 applications where I can run this board. So the first application I'm going to take a look at is with the shielding. You sort of see the copper layers right there and the transparency. So the first thing I'm going to point out for those who are unfamiliar with what flow simulation is, it's a CFD tool. So CFD stands for Computational Fluid Dynamics, and it's kind of a it can do a lot of different things. So in this case, we're looking at thermal management and how it integrates with electronics cooling, but it can also look at pipe flow and a variety of situations. One of the great things about flow simulation is it's integrated into your CAD. You know, right here, right within SolidWorks, we're dealing with an assembly. I can run flow scenarios or board scenarios for single body parts if you're just looking at maybe an IC itself, or maybe you want to look at the entire assembly, which is this case right here. So I'm going to step you through a sample project, kind of show you how easy it is to set up, and then we'll take a look at the results for both of these scenarios. So everything within flow simulation is done through the wizard. The great thing about this wizard is it's a very nice and efficient way of setting up these projects. In terms of ease of use, flow simulation is one of the easier CFD codes out there to learn. It's very easy to hit the ground running just with a little bit of training to sort of solve these types of problems. So the first thing you see right here is I can set the project name. I can also, since I'm working within SolidWorks, I can take advantage of configurations. And so in this case, we're looking at our PCB. I might actually have multiple components. I might have resistors, etc. And I might want to try different configurations. Maybe I have a heat sink, and I want to sort of rotate that heat sink. So I can take advantage of different configurations. Lots of different units I can utilize, and I can customize it how I see fit. So maybe I want to work in Celsius or Fahrenheit. Whatever I really want, I can sort of customize on the unit side of things. Now, in terms of this scenario, it's an external flow study because it's an engine that's allows air to be circulating around it. Internal flow would be if everything's watertight and you want to know what's happening on the interior of your part. So you have two different types of analysis studies you have the ability to run. Additionally, you have all modes of heat transfer available to you within flow simulation. So in this case, we have convection and conduction, but if I wanted to, I could also apply radiation for our scenarios. And lastly, we could run our scenarios as time dependent or steady state. So I've run an example of each in this scenario. So the first one we're running is a steady state scenario. So in this case, I need to turn on heat conduction and gravity to consider natural convection, and then I hit next. The other thing to really point out here, especially some of you working in some specific industries, you're not limited by just air in terms of the gases. You have a whole bunch of different gases you can utilize, as well as a bunch of other different types of fluids. So maybe not for thermal analysis, maybe you might even have a board or something that's watertight and it's surrounded by a fluid, and you want to see how that fluid is cooling the box. You have the ability to apply liquids. So that's kind of really the great thing about flow simulation. So in this case, we're running air, and then we can specify our default material. So this is what the majority of your prevailing materials in your model. So in this case, I just said it was aluminum for our engine. Lastly, we can specify our roughness conditions and then what our initial ambient conditions are set at. So with that being said, once I create a project, it's just a matter of keying in the specific boundary conditions for this application. So like I said, the motor itself is being modeled as aluminum, but we have a couple other components. So you see we have our IC right here, and we can actually click on individual components parametrically and select what type of material it is. So in this case, I'm just specifying the semiconductor, the IC, just clicking on it and saying it's silicon. I did the same thing for the two copper layers you see right there, where I just right-click on it and specify both of these are, you see the copper layer as copper. Now, the real pertinent thing in this problem is we're looking at thermal management. So we have some heat power that's being derived. So in this case, the engine itself is generating 10 watts. It's a smaller engine, so about 10 watts, and that's going to be one of our drivers to the problem, as well as we have a volumetric heat generation rate on our IC at 0.192 watts per meters cubed, and that's just from the IC spec. One of the other really cool things about this is we're working with a PCB, so you're coming from PCB, and I can actually use a printed circuit board, and that's one of the features of jumping up to electronics cooling. So if I look at this right here, I can actually specify, what type of board it is, how many different types of layers there are, and let's take a look at the actual material properties for this board. So if I look at the item properties, I see my material density, my conductor material density, how many layers there are, and I can really get really custom in terms of what my PCB is on the thermal side of things. The other thing I'll point out here, one of the great things about it is with electronics cooling, you can actually specify current or voltage on different faces. And we all know that those different values are going to influence heat. So you see my electrical conditions. In this case, we don't have that, but I just want to point that out, that if you have a current or a voltage or even a contact resistance, you can key that in. Additionally, if you have any heat pipes or 2-resistor components or thermoelectric coolers, that's something also that's available within the electronics cooling module to really customize your boards accordingly. So in this case, when we look at our scenario, this is our first case, this is our steady state scenario, we look at our results and we can actually look at our board and look at what our temperature is, but we can also look at our IC. So we look at our IC right here and we see what our temperature is. Okay, great. So we record those temperatures, and now we might want to see what our temperature value is at. We want to see what the effect is without the actual copper layers. But before I transition to that, I ran this as steady state for both scenarios, but I also just wanted to give you guys a glimpse of what you could do with the transient scenario. So say you're really concerned about how much something is heating up with respect to time. All I would have to do is just specify this as a time-dependent problem, and then key in the amount of time. So you see right here, I'm running this for 1 hour, so 3,600 seconds. And you have total flexibility on your control, meaning that I could actually save, in this case, I'm saving results every minute. I could actually say every 10 seconds or 20 seconds, whatever you want to do in terms of the transient scenario. And the great thing about this is you see all the same boundary conditions, but for those of you who are working with switches or anything that's turning on and off, I could actually turn off these heat sources to be with respect to time. Maybe they're only running at 50% efficiency for 30 minutes at the time, and then it jumps up to 75% efficiency. If I wanted to, I could actually key that value in. So if I go right here, you see this toggle button. I could have a dependency that says it's a function of time, or even a function of an equation. So maybe it hits a certain temperature, it turns off. Really, anything you would be applying in the real world, you have the ability to sort of apply within the flow simulation context. All right, so let's take a look at these results. And this is our transient scenario. So I just want to point out a couple cool features. So one of the really great things about looking at a transient scenario is you'll be able to look at how those results are differing with respect to time. SOLIDWORKS has a lot of different animation tools. The one I'm showing you right here is the Transient Explorer. The Transient Explorer can be saved out as an animation, but there's also some actual custom animation plots you can actually hear where you set your frame rate and you can really customize your animations accordingly. So I don't know, maybe I want to look at the board temperature and how much it's changing with respect to time. And you see I have a legend right here and I can move it. That legend is going to change. So if I could update it at each different time point, you see how I can change the temperature, be at 72 and then kind of works its way up in the system. Maybe I adjust it to be 75, and you get the picture in terms of really getting total customization in terms of time. So the overall sort of scenario in this is if the steady state scenario where, if I come back to this, we see that what our temperature value is at for the IC, which is at 46 degrees. This is the 2 copper layers. So now we want to try the other scenario that Mark sent me. So let me open that up. And the really great thing about this as well is because this is integrated into the SOLIDWORKS portfolio, you can really take advantage of PDM if you have that available to you, and really being able to really store and utilize your data efficiently. So when I open up this project, the first thing you see is I got rid of those layers right there of copper. It's one less solid material. Otherwise, the boundary conditions are the same. You see the 10 watts for the motor, 0.192 watts per meter cubed for the IC. So when I run this scenario, actually, if I look at the results, you see that the temperature, and let me change, kind of the other really great thing about this is I can change the units on the fly. So say I don't want to be in Fahrenheit, let me go to Celsius. You see where my units are at 44 degrees C versus 46 degrees C. So really thinking about, running both of these scenarios, I can run a lot of different scenarios and really check what's happening on the board. So with that, I am going to turn it back over to Mark.
Thanks, Drew. Are you able to pass me?
Yeah.
Thanks. All right, so in conclusion here, what we've seen is our design intent was we needed that IC to perform optimally. And by the data sheet, that actually performs optimally at 25 degrees C. And between our two cases, what we found is that copper layer is actually sinking heat towards the IC. So not the behavior we want, and that our temperature ultimately for that steady state value is going upwards of 45, 46 degrees C. So essentially, we're not going to want to have that shielding act as that sink towards the IC, which basically means the unshielded case, we're going to have to relocate that board to a less noisy area and basically get it away from those supply voltages from our panel. So ultimately, the takeaway here is when it comes to validating our design, we were able to do so before even having to board spin, right? Not only were we able to ensure fit and function because of our ability to collaborate with our mechanical designer with board shape, hole locations, and so on, but we were also able to validate that thermally. And ultimately, once you're in that mechanical environment, you get to use those mechanical tools, so you can improve your documentation outputs, the time to output as well. So this really concludes the presentation portion of this webinar.